So first, let's finish our discussion on trees. Okay. So then we'll do the past paper discussion on distributed databases. Okay. Right. So now we have discussed this finding minimum, finding maximum, traversing, depth first traversing, the three approaches, breadth first traversing. Okay. And also how to delete nodes, right? When we have no your node to be deleted is a leaf, node to be deleted has one child, and the node to be deleted has two children. Okay. Right. So then we were discussing about the use of binary search trees. So obviously the main usage is searching, right? It's part of binary search algorithm, one way of implementing binary search. Right? If it is balanced binary search tree, the worst case is log to n. But in case it is not balanced, the worst case is getting into the pathological tree where data is already sorted. Then of course it is ON. Okay. So I just updated this slide. I will upload the updated slide. Okay. I just updated this slide to make it a little bit more clear, because remember, if it is balance only log 2n, right? Otherwise, it is less than log 2n. It's between ON and log 2n. The, the worst case is it's not balanced, as well as you enter data already sorted. So then, of course, what you ended up in a linked list or pathological tree. Okay, right. So other than that, there are a few more usages. Okay, of course, there are so many usages, but we only look at two or three usages, right? One is obviously the binary search tree. The second one is you can use binary tree or binary tree, not a binary search tree, binary tree, to convert infix expression to postfix or prefix expressions. Okay. So remember, when it comes to stack-based process architecture, if you want to evaluate an expression, we first convert it to postfix and then use stack to process it, right? Then use stack to process it. But first you need to convert it to postfix, right? Because what we write is infix expression in our Java program, Python program, right? For example, A plus B into C plus D. So this is infix. So we know that the postfix one is A, B plus C, D plus multiply. But how to do that? Of course, as a human, right? As an intelligent person who know the logic, we can do it. Right? But for computer, you need to give it the logic, right? Because computer just execute what we have instructed. So how can we instructed the computer to convert infix to postfix? Because then only stack architecture can be used to evaluate this. Okay. So one approach is you enter your infix expression into a binary tree. Binary tree. Okay. So then you do, if it is postfix what you need, of course, that is what we need in stack architecture, you do a post order traversing. So the result is you convert infix to postfix. Okay. For example, this one, if we put it into binary search tree, it will be something like this: A, B plus C, D minus, sorry, that is also plus. And those two you need to multiply. Right? Those two you want to multiply. So this is infix, A plus B into C plus D. Now let's do a postfix, post order traversing. So post order is left, right, current. So let's start with root. Left, recursively left, left, right, current. So that means A. Now we count to the left. Now we are going to the right. Left, right, current. Now we have done left, right. Therefore, this is current. Now we have done left. Now we are going right. Recursively going left. Recursively going left, right, current. Right. So now we have done left. Now we are going right. Left, right, current. Now we have done left, right. It is current. And here we have done left, right. It is current. You can see what we get is postfix expression. So you put your infix expression into binary tree. So then do the postfix, post-order traversing. What you ended up is postfix notation. Now we can now we can write the logic. Put it into a binary search tree and do the post-order traversing, right? Even we wrote the post-order traversing recursive code. So what you ended up is postfix expression. So during compilation or during execution, your infix expressions are converted to postfix. Then only it is being executed, right? So that is another use of binary trees, converting infix into postfix. If you want to convert it to prefix, you do the pre-order traverse, right? And again, if you do the in-order traversing, you ended up with your same infix expression. So when your expression is in binary tree, pre-order traversing results in prefix notation, post-order traversing results in postfix notation, in-order traversing results in infix notation. Okay. Okay, that is very simple scenario. If you have brackets and so on, things are a little bit more complex, but let's not get into that complexity. But you must have that now the idea that this is the use of binary trees facilitate you to do these conversions, right? Programmatically. Right. So now we are moving into our next subtopic, balance binary tree or balance binary search tree or whatever. Okay. But it's basically balance binary tree. Or we can say balance binary search tree. I think better word is balance binary search tree. That means it's balanced and sorted from left to right. Right? Sorted from left to right. So I told you that this when you do a search on binary tree, it is log to n if it is balanced binary search. Otherwise, it can even get into ON. So what is mean by balanced binary search? So balanced binary search tree means when you insert data to a binary tree, right? Binary search tree, we always keep it balanced because otherwise there can be situation where one side is longer, the other side is shorter. So then your binary tree become more like a linked list. More like a linked list, may not be 100% linked list. Of course, there's one possibility of getting linked list also. That is, your data is already sorted, ascending or descending. So then when you add it to the binary search tree, you ended up in a pathological tree. Or basically, you ended up in a linked list. So then you don't have that advantage of a binary search tree because you ended up in a linked list. So how to prevent that? So ended up with a linked list is the worst case. Or you will end up with something like this. You see, this side is highly lengthy. This side is not that length. So therefore, the worst, if you are searching something like this, you need to come like this. But if you can balance it so that left and right, it's grow in a more balanced manner, we can reduce the number of levels. So lesser the number of levels means we can do the search faster. Because search always start from root. Okay. So if you keep balancing, you can do any search within log 2 and worst case. Okay. So how do you balance? So the best thing is the moment you lose your balance, you fix it rather than wait. rather than wait and balance it later. Right? So you insert and check whether it's balanced. If balanced, yeah, you are done. No, nothing to do. But if it is not balanced, you adjust it, balance it. Again, you insert. Again, check whether it's balanced. Yes, don't do anything. But if not balanced, do the balancing. So rather than you wait for long unbalanced tree and then fix it. Okay, so that is the strategy. So there are different techniques to do that, different algorithms. So the two most popular algorithms are ABL trees and red-black trees. ABL balanced binary search trees, red-black balanced binary search trees. So out of those two, the easier to understand is ABL tree. Red-black tree is also not a very difficult thing, but it's not mentioned in your syllabus, and there has been no question so far from red-black tree. So therefore, I will only do ABL tree. Okay, assuming that examiner will not ask anything about red-black tree because you also have a capacity, right? You can't. It's a headache if you want to learn so many things, right? So therefore, I try to give you the minimum required. Right? So ABL trees anyway you need to understand because there are past paper questions. Okay? Right. So therefore, we will only look at ABL balanced binary search tree. Right? ABL approach. But just remember in MCQs, they might ask another approach is red-black tree. Okay. But we are not going to cover that. Right. So how does ABL balanced binary search tree work? Or how do we build ABL balanced binary search tree? So we use a concept called balance factor. Balance factor. And if the balance factor is satisfied, we don't do any adjusting. But if the balance factor is not satisfied, we balance it. So that is the idea behind ABL balanced binary search tree. Okay. Right. So what is mean by balance factor? It's very simple concept. So balance factor is balance factor is for any node. For any node, you can calculate the balance factor. Okay. Any node, including the root. So how do you calculate the balance factor? For a node, it's the difference between height of the left subtree and height of the right subtree. Right? Height of the left subtree and right subtree with respect to that node, not with respect to the root. Because balance factor can be calculated for any node. Okay. Height means, for example, if it is a leaf node, obviously balance factor is 0 because there's no left child, right child. So here also height 0, here also height 0. For all the leaf nodes, balance factor is obviously 0. Right? So balance factor 0, -1 or +1 is okay. But if it is bigger than anything, oh, like -2, +2, +3, -2, -3, that means it's unbalanced. You need to do the adjustment. But if it is 0, 1, -1, you don't need to do anything. Obviously, leaf node, you don't need to do anything because always balance factor is 0. Now, if you take something like this one, height of the left subtree is 1 because you have 1. Height of the right subtree is 0 because no right child. So therefore 1 minus 0 is 1. 1 is fine. 1 is fine. So here of course 0, here 0. Here both 1. 1 and 1 is 0. So this is fine. Okay. But what about this? Height of the left subtree is 1, 2. Height of the right subtree is 2. Height of the left subtree is 0. 0 minus 2 is -2. -2 is outside this. So that means we have violation here. We have violation here. Here also no violation because height of the left subtree is 1, 2, 3. Height of the right subtree is 1, 2. 3 minus 2 is 1. 1 is okay. Now in this binary search tree, now we have a violation Violation is in this particular node. So now we need to adjust this, right? Balance this. So likewise, whenever there's a violation, we balance it before inserting the next one. Okay, is it clear? Sometimes there can be more than one nodes which are not unbalanced. Okay, so we always check the balance from bottom to top, bottom to top. So therefore, if this is not balanced, this is not balanced, we fix here, not here. Okay. So then still if it is not balanced, only you come and again fix it here. Okay, so you need to understand it. Once you understand, this is very easy. Otherwise, this is like a hell, right? You may feel like it's very complicated. No, it's not complicated if you understand it. Okay, and clarify any questions. So balance factor is the height of left subtree minus height of right subtree. If the value is 0, -1, or +1, that is fine. If it is bigger than that, it's unbalanced. That's it, right? That is called balance factor. So we can calculate balance factor for any node. For example, here height of left subtree is 1. So you know what is height, right? We discussed that last week. And here 1, 1 minus 1 is 0, no issue. But here you can see height of the left subtree is 0 because no children, no, okay. But height of the right subtree is 1, 2. So 0 minus 2 is -2. -2 is outside this range. So that means this has violated. So if there's a violation, you need to do a rotation, right? You need to do a rotation, one rotation or two rotations. So we call it, sometimes you can do single rotation and fix it. Sometimes you need a double rotation. Okay. So how do you fix this? How do you make it balance again? By doing rotations. One rotation or two rotations. In some cases, one rotation is enough. Some cases you need to do two rotations. Okay. So we do the rotations to those unbalanced nodes only, and we check the unbalancedness from bottom to top. For example, when do you check the unbalancedness? For example, when you insert, say you insert a record here. Now only it is unbalanced, right? So therefore you check it from this point on upwards. This point upwards. So adding a node here is not going to unbalance these things. Only up to this, these are not going to be unbalanced. So then the first one you found that unbalance, you need to fix it. So in this case, this is 0 balance factor. This is 0 balance factor is 1. Here balance factor is -2. So therefore you need to fix here. Okay. So you check it from your newly inserted node upwards. Okay. Right. As I told you, there are two type of rotations. Two type of rotations. Right. So don't confuse. I told you sometimes you can do single rotation. Sometimes you need to do two rotations. Right. Sometimes you need to do one rotation. Sometimes you need to do two rotation or double rotation. So at the same time, there are two type of rotations. What are those two type of rotations? Either you need to do left rotation or right rotation if you are doing ABL adjustment. Okay. Left rotation or right rotation. So remember, sometimes you need to do two rotations, right? So therefore, maybe sometimes just your left rotation is enough. Your right rotation is enough. But that is, you are doing single rotation. That single rotation can be either left rotation or right rotation. But sometimes you need to do double rotation. So then maybe you need to do a left rotation followed by right rotation, or right rotation followed by left rotation, or sometimes even left rotation followed by left, or right rotation followed by right. Okay. Right. First, you need to understand what is mean by left rotation, what is mean by right rotation. Okay. So basically, right rotation is the reverse of the left rotation. Left rotation is the reverse of the right rotation. So therefore, it's very easy to remember also. Though it's two rotations, one is the reverse of the other. Right. So let's assume this is a balance. So this is a binary tree, binary search tree. You can see it's sorted A, B, C, D, E sorted, right? Therefore, this is part of a binary search tree. Forget about the balance factor. Let's assume we want to balance it. Sorry, we want to rotate it. Rotate it. Let's say I want to rotate it in this point. First of all, is this a unbalanced one? This balance factor is zero. Balance factor is zero. Balance factor is zero because 1 minus 1. Here balance factor is 2 minus 1, 1. Here balance factor. Actually, this is not unbalanced, right? And all the nodes are balanced because it's either 0, minus 1, or plus 1. But let's assume this we want to do a rotation because here our objective is learn by how to rotate. So how to do the left rotation? So left rotation, sorry, how to do the right rotation? Right rotation means we rotate to the right side. So this is how you do it. Say, let's say we want to rotate to this point. Whenever you do a rotation, you have a pivot point. You rotate on that point. Let's say pivot point is D and we want to do a right rotation. This is how you do it. Right? So your D will go down, B will come up because we are doing rotating like this. Right? B will go up, D will go down. You can see B has come to this point and D has gone down. And when B comes up, A also comes up because A is the left child of B. And when D goes down, your E also going down because E is the right child of D. Right? So when we rotate like this, when B goes there, A also comes. And when D goes down, E also going down. But there's a small thing here. What happened to the C? Earlier, C was the right child of the B. But now B is here. B is here. So when you do right rotation, make sure this guy's right child becomes this guy's left child. So therefore, this B's right child is now D's left child. This is the thing you need to remember, understand. Right? So that means this child passed from left to right during that rotation. Other than that, it's simple rotation, right? So this goes down, this goes down, this comes up, this comes up, this comes up, this goes down, this goes down. But while you are doing this, make sure this guy's right child is now this guy's left child because this guy goes down. So why do you want to do that? Because otherwise we lose our sorting order from left to right. Now it's again sorted A, B, C, D, E. Okay. A, B, C, D. Is it clear? Okay. Is it clear? That is called right rotation. Okay. So the left rotation is you are doing it in the reverse order. Left rotation. So now what happens? B comes down. When B comes down, A also going down. Right? Because A is the left child of B. And D goes up. When D comes up, E also comes up. Right? When D goes there, E also comes there. But this left child of D must be connected as the right child of B. So this C is the guy that must be taken from this side to the other side. Now the left child of D, we must connect this as the right child of B. Okay. Because remember earlier in this rotation, we passed this to this. Now we are taking it back, giving it back to this guy in the reverse process. Reverse process. So you can see this C is going from B to D, and again you are getting D to B. because this is the reverse process. And again, sorting order is preserved, right? A, B, C, D, E. So those are the two rotations. We don't do anything else. All your balancing is done by either left rotation or right rotation. Okay. Left rotation or right rotation. Nothing else. But whenever you do the rotation, make sure you know on which pivot you are doing this. Okay. Right. So those are the two type of rotations. You don't do anything other than left rotation and right rotation during balancing. So which rotation you are doing? Yes, I will explain the scenarios. When to do left rotation, when to do right rotation. And remember, I told you sometimes you need to do single rotation, sometimes you need to do double rotation, right? Now I'm going to explain that. Okay. Right. In order to explain that, we'll take few scenarios. Right. So what are the scenarios? Possible imbalance scenarios. Okay. That is, the first one is we have this kind of a scenario. Okay. We have this kind of a scenario. And you can see that this one's balance factor is 0 because these are not nodes, okay? This is just to make it nice. This is a leaf node, okay? So therefore it's 0. This one's balance factor is 1 minus 0, 1, fine. This one's balance factor is 2 minus 0, 2. This is not balanced. So therefore you need to fix it here. And this is called left-left case. Because left, this is the pivot point. The issue is left situation. Right? If you have a left situation imbalance, because this is 2 now, you need to do single rotation. That rotation is a right rotation. That rotation is a right rotation. And assume these are some sub-trees also, okay? So how to do that? So this goes up, this goes down, this also comes up with this. But remember, you need to pass this C, the right child of this guy, as a left child of this guy. That is super important. Okay, so you can see that now 4 has come here. With 4, 3 has come. And 5 has gone down. Remember the right child of 4 is now left child of 5. You can see C here. And now C is here. So that is a must. So this is a right rotation that convert this into this. Right? 5 goes down, 4 goes up, 3 goes up, but the C is now the left child of this. This is the critical thing. So this is a single rotation, and now we have make it balanced because this is balance factor 0, balance factor 0, balance factor 0. So that is how you fix left scenario. Left scenario. Right? So that is this one. Right? How to do that? Do a right rotation. Right rotation. So then you get balance. So if you get a right scenario, right, this is left scenario, right scenario, like this. Now the balance factor issue is here because this is 2 minus say 0, 2. Sorry, 0 minus 2 minus 2. This is the issue now. So now you need to do left rotation. So then 3 goes down, 4 comes to the pivot, 5 also goes up, but make sure this guy is given as this left child of 4 is now right child of 3. You can see B. So that is how you fix right scenario. Just do a left rotation and it will be balanced. And this is how you fix left scenario. Do a right rotation and it will be balanced. Okay. Is it clear? It will be further clear when we do a real example. So there are two more scenarios, which is unbalanced. What about this? So this is fine, assuming only same level of children, that is 0. This is fine because this is 0, -1, -1. -1 is fine, but this is the issue. You can see 2 minus 0. 2 minus 0 is 2. 2 is outside that range. So if you get into this kind of situation, we call it left right. You can see issue is here. Issue is here. And the scenario is called left right. Or sometimes we call it dog foot. Dog foot. Balu kakula. You may have seen that the dog foot is like this. Right? Ballan kakul menu adaitika. So sometimes, especially in your exam papers, they call it dog foot scenario. But I prefer to, then of course, this is also dog foot, this is also dog foot. So therefore, we can't distinguish it. So therefore, I prefer to call it left, right, and this is left, left. Okay. And this one has right, left. That is also issue. Right. So how to fix this scenario? Because this is now imbalance, left, right scenario. So this is where you need to do double rotation. Right? Double rotation. First, you do a left rotation and convert this to this left-left scenario. Remember, left-left is still imbalance, but this is how you do it. First, we convert it to this or left-left by doing a right-left rotation. And then you convert it to balance by doing a right rotation. Okay. So how to convert this into this? Just normal left rotation. Left rotation. Right. So how to do this left rotation? So you do the left rotation, right, on this point. Okay. Yes, issue is here, but you do the rotation here. So that means your 3 will go down and 4 will come here and 5 remains there. Okay. And remember, this is the left child of this guy. So this must be passed to this guy as a right child. So therefore, this left child of 4 will be the right child of 3. ඔන්නෝ තමයි මතක තියාගන්න. හැමතිස්සෙම මේ පැත්ත එක්කෙනාව පාස් කරන්න ඕනේ මේ පැත්ත එක්කෙනාට. නැත්නම් මේ පැත්ත එක්කෙනාව අර පැත්තට පාස් කරන්න මොන රොටේෂන් එකක් කරත් ඔය පාස් කරන්න වෙනවා එක නෝඩ් එකක්. පාස් කරේ නැත්නම් වැඩේ වැරදි. Okay. So therefore, this kind of a situation, that is left right, you first convert it to left left by doing a left rotation, but left rotation on this point. Yes, issue is here, but you do the left rotation on this point. Then you do the right rotation on this point. And then it is balanced. So that is why we say double rotation. First you do a left rotation to come to this point. Then you do a right rotation to make it balanced. But if this situation, you just need to do a right rotation and you are done. And here also, right, you just do a one left rotation and you are done. But if you have right-left situation, the second dog foot scenario, first you do a right rotation to make it right. So then 4 goes up, 5 goes down. Make sure you C is given to the 5. Okay. Then you ended up with this by doing the right rotation on this point. Issue is here. And now you do the left rotation on this, right, and make it balanced. Right. So now you know that there are two types of rotations: left rotation, right rotation. And there are 4 scenarios. This scenario you can convert it to balance by doing a single rotation. But this scenario you need double rotation. First you convert it to this and then you fix it. This scenario you can fix it by single rotation. But this scenario, first you convert it to this and then you convert it to this by doing 2 rotations. Now we are done. The theory is done. Okay. Anything you want to clarify? Maybe when I do the example, you will further understand.
The,
Yes.
so for every insert, we need to check whether this case can happen,
Yes. After
isn't it?
every insert, you need to check whether any of these 4 scenarios are there, because all these 4 scenarios are imbalanced. If this kind of scenario, you do a single rotation and fix it. If this kind of scenario, you do your double rotation and fix it. Okay. After every insert, you need to check it. Because the idea is, rather than make it like a cancer, right? Rather than make it worse, whenever there's a first symptom, you fix it. You fix it. Okay. But it doesn't mean that always you need to fix it, because sometimes it's all fine. After insertion, still it is balanced. Okay.
So what is the extension of ABL?
I think I'm not very sure. Maybe the people who came up with this idea, I'm not very sure. I think because the red black, of course, we mark them as red nodes and black nodes. Maybe the people's first names. Okay, let double check with ChatGPT. Maybe the guys who came up with this idea. AVL stands for. Yeah, so these are the guys who came up with this idea. Okay. Adelson Welsky, AV, and third guy is Landis. Right? 3 guys get together and found this issue. 1962, not very old, right? But not very long ago, right? Only about less than 100 years ago, right? About more, little bit more than 50 years, right? Maybe. Right? So these 3 has come up with this idea. Right. So let's take an example. So you should be able to understand this by after end at the end of this example. Okay. So let's keep inserting our data. Okay. Right. So we want to insert 50. Remember what we are building is a binary search tree. But after every insertion, we need to check whether it's balanced or not. If not balanced, fix it. How to fix it? Either by doing single rotation or double rotation. So these single and double rotations can be either left rotations or right rotations. Right. So insert 50, then obviously 50 is your root. Of course, it's not imbalanced, right? Because balance factor is 0. Let's see. Now we want to insert another data. 30. So 30 is less than 50. So therefore 30 will be the left child of 50. And no issue, because here balance factor is 0. 0 minus 0. Here balance factor 1 minus 0, 1. 1 is 5. Minus 1 plus 1, 0 is 5. Now let's insert another data. I want to insert 20. So 20 will be less than 50 and less than 30. So that will be the left child of 30. And now all of a sudden, now once you insert, you check the balance factor from bottom to top. Okay. Because you just inserted this. Now from this guy, you come towards the root, checking the balance factor. Now this guy's balance factor is obviously 0 because it's a leaf. This one's balance factor is 1 minus 0, 1, fine. But what about this guy's balance factor? 2 minus 0, because right hand side 0 height, left hand side height 2, 1, 2. So 2 is violation. And now you can see that it is left-left situation, right? Mega Mahamaru there, left-left situation. So left-left situation means you can fix it in single rotation. බලු කකුල් තමයි දෙපාරක් rotate කරන්නේ. කකුල ඇද අයින් කරලා තමයි හදන්නේ. දැන් කකුලක් ඇද නැහැ. So therefore this is a left-left scenario. Left-left scenario means you need to do a right rotation on this. So then 30 goes up, 50 will come down, 20 will also comes with 30. and මේ පැත්තේ තියෙන මුකුත් නැති හන්ද එයාට පාස් කරන්න මල්ලක් නැහැ. මෙතන දිනුන නැහැ පාස් කරන්න ඕන මෙයාට. then nothing to pass. Simply 30 will go there, 20 will also come here, 50 will go down. And now it's balance. Right? This is not rocket science. So now we have done a right rotation and fix it. Now it's back balance. Right? Now our binary search tree is again balanced. Now, usually when you do a build a binary search tree, always your first one is the root, right? But now root can change because we change this, we balance it. Okay, so therefore nodes can change. Right. So now this is our situation. So now let's see, we want to insert another data. So definitely that is not going to break our balance because either it will come here or come here, right? It's not going to do any violations. The 80. So 80 will be right child of 50. Now here balance factor is 0, fine. Balance factor is 1 because, sorry, 0 minus 1. Actually, this is balance factor is minus 1. And this is balance factor is 1 minus 2 minus 1. So that is fine, right? So obviously this one is minus 1, okay? Let me fix it. Because left minus right. Okay. So I just fixed that issue also. But this is not an issue, right? Because 0 is fine, minus 1 is fine. So this is still balanced. So if it is balanced, you don't do anything. Now this insertion, you don't need to do balancing. So therefore now we can do another insert. So let's say we want to insert 70. So 70 will be inserted to what? Bigger than 30, bigger than 50, lesser than 80. So it will be something like this. Now definitely it's going to violate. Which one is violate? This is fine 0, this is fine 1. This is now violate.
Sir,
Yes.
what is the meaning of balance factor?
So balance factor is height of the left tree minus height of the right tree. Okay. Height of the left tree of that node minus height of the right tree. Okay. So now after inserting 70, of course this one's balance factor is 0. This one's balance factor is 1 because 1 minus 0, fine. This one's balance factor is minus 2 because here 0, here 1, here 2. 0 minus 2 is minus 2. So therefore this is now violated. This is also violated, but remember we are interested in going up and we are looking for the first violation. So therefore we are not in, this is also violated, but we are interested in this one. Okay. Okay. So now there's a violation. This is also violated, but I have not marked it as red because this is the first one to fix it. Sometimes when this is fixed, this will be okay. Okay. So don't think that always after fixing this, I need to fix this. Sometimes when this is fixed, this will be automatically fixed. But don't fix this, right? You insert here. So you check the violation from that node upwards. So those are the small things. Sometimes what happens is students fix it here, thinking that, okay, this is also minus 2. No, it doesn't work. There's a systematic approach. Right now, this is the violation. And check what kind of violation is this. Right. So this is the violation point, and you can see it's right, left. Second scenario of dog foot. Whether you like it or not, you need to do double rotation now. Because this is right, left. There's no shortcut, right? Not a ketty vidhi naha. So therefore, now you need to do the double rotation. First, you do a right rotation to make it right, right on this. So then you do a left rotation on this to make it balance. මතකනේ first rotation එක කරන violation එක තියෙන කෙනාට යට එකනට second rotation එක තමයි හරියට එතනට වේද දෙන්නේ. So now we are going to do a right rotation. So then 70 will come here, 80 will go down. Simple as that. But that is not the end final result. Right now it is a right? You can see now 70 has goes there and 80 has come down. Still this is violated. Still this is -2 and still this is -2, but this is where the issue is. Now this is right situation. Right situation. In right situation, you do the left rotation on this point now. So then 70 will go up, 50 will go down, 80 will also come up. Simple as that. Now you can see that it's balanced again. So balance factor is 0, balance factor is 0, balance factor is 0. And now this one's balance factor is also fixed. Earlier it was -2 because this is 1, 2, 3, 3 minus 1. But now it's again 2 minus 1 minus 1. Minus 1 is fine. So therefore now it's fixed. So you can see when I fix this one, this is already fixed now. But don't fix here when there's an issue here because you are checking from bottom to up where you insert and bottom to. And the other thing is you don't need to, if you insert something here, there won't be issues here because we are doing changes to this side. And when you are doing changes to this side, you don't need to worry about this side. Okay. So otherwise students waste their time. So you insert somewhere here and you check here also. No, you don't need. Right. So this is our situation now. And likewise, you keep doing this. Keep doing this. Right? Even though your tree has 1,000 reports, 1,000 nodes, you keep doing this. Okay.
Sir,
Yes.
what is the practical advantage over other trees compared to balance tree?
So that is what I already mentioned, right? You also you can tell me that now.
It's in order.
No, order is always there, right? For example, uh, first we insert it preserving the binary search tree, right?
Yes.
So the practical advantage is we don't let it grow like this, right? Then you don't get the log2 and search. Worst case log2 is not bigger.
Understood,
Worst
sir.
case is worse than log2 n then. Okay. Now you can see
Got it, sir.
if you search 50, maximum you need to go 2 points and you found it. If you are searching 20 in single hop, you found it. 70 single hops, you found it. 80, you can see maximum 2 hops. 1, 2, 3, 4, 5. Right? 5 nodes. Log 2, 5. 5 is not a binary, 2 to the power, so therefore it will be 8. Right? So that means log 2, 8 means 2 to the power 3. So maximum is 3. 1, 2, 3. You don't need to go beyond 3. But let's assume you insert it without doing balancing. So first we inserted 50. Right? So then we inserted 30. Then we inserted 20. Then we inserted 80. Then we inserted 70. Now luckily, even without balancing, this is fine. Because here balance factor is 0. Balance factor is 1. Balance factor is 0. Balance factor is 1. Balance factor is 0. So therefore, this is a very special case, right? You can see that even though you don't do the rotations, by luck, we ended up in a balanced binary tree. But that is not always the case, right? That is not always the case. For example, if I add something like 10, 20, 50, 30, right? 40. Now what will happen? Of course, if you do it like this, AVL tree, always you will end up in a balanced approach. But now if you don't do like that, what happens? 10, 20, 50, okay, 30, 40. And so 10, 20, 50. Then of course 30 is bigger than 20, lesser than 50. Then 40 is bigger than 10, bigger than 20, lesser than 50, bigger. Now you can see you have ended up in a linked list. So if you to searching 40, you have to search 1, 2, 3, 4, 5. But if you do a AVLT, definitely it's not 5. It will be something like maximum 3 hops, right? That is why we want to keep it balancing, because these kind of scenarios will ended up in a very long binary tree. Actually, this is a linked list effectively, but balanced binary, if you do it like a AVL tree, definitely you are going to end up something like this. Okay. That is why we are doing this. Okay. Right. Shall we do a past paper question? Little bit old paper question, because these days they have asked mostly in MCQs. I like to do a second paper question. So these are easy questions, right? In order, pre-order, post-order traversing. And so this is not asking for balanced binary trees. So this is moving to linked list. Yeah, this is AVL tree. You can see create a AVL tree. This is 2019. Okay, I do this. Create a AVL tree for this one. Right, 6 marks. And you need the final answer only, but you need to get into the answer gradually. Otherwise, you can't do magic and get the final answer, right? There's no magic. You gradually do it and get the final answer. Quickly do it. Take 2 minutes. So you keep inserting, keep checking the balance factor. If required, do a single rotation or double rotation, depending on the situation. You can't do whatever you like. You must do the proper solution. Okay. Look at the situation, fix it according to the logic. So by doing these things, your IQ is also going to be increased, right? Capacity is going to be increased, and you come up with different ways of problem solving, and your fear will go die down. Fear of solving problems, because you will feel like, okay, I can handle this kind of complexities, and also you think recursively. So basically, build your capacity, make you ready for career in engineering. So engineers do hard things. Engineers go and face challenges where the ordinary people are afraid of going. And do it fast, right? So remember, you have 2 hours for both MCQ and structured essay, right? 2 hours for both. So second paper, you have only 1 hour. So one question, 30 minutes. One question has about four or five subparts.
So what is the meaning of an ABN?
So I showed you about 5 minutes ago, right? So those are the three guys' starting names. The starting letters of the three guys' names. Now in this question, they say draw the final answer, but some papers, they have given marks to steps. Each and every intermediate steps, you get marks. Okay. So then it's better, then at least you can collect some marks. Now here, if your final answer is wrong, you get 0 marks because they say just draw the final answer, right? But of course, you can draw the intermediate answers. Anyone got it?
Yes, sir.
Yes. So I will draw it now. Not bad. So I just want a white background, okay? So let's start drawing. Right. So I'll add 15. No need of any rotation because that is our first one. Okay, so then I can add 20, 15 and 20 here. Just give me 1 minute. I want to plug in my power cable, okay? Okay. Right, so still it's not issue. Still it's balance. Right, so this is fine. This is fine. Now I want to add 24. 15, 20, 24. Now it's not balance because this is balance factor 0. The balance factor is 1 minus 1 minus 1. That is fine. But here 0 minus 2, because this is 2, this is 0. 0 minus 2 is minus 2. So this is violated. And this is right, right. So that means you need just single rotation. Left rotation. Left rotation. Mark karana mein agar rotate karana. So then the result is, or you can say left rotation. Okay. So then the result is 20 is here, 15 is here, 24 is here. Now it's balanced. Now it's balanced. Now you need to add 10. So 10 is here. Let's draw it separately. 20, 15, 24, and now 10 is here. That is fine. This is 0, balance factor 1, balance factor 1, balance factor 0. by balance factor 1, 2 minus 1 is 1. So this is balance. Now we can add 30, 20, 15, 10, 24, 13 is less than 20, less than 15, bigger than 10. Okay. Now you need to check from here upwards. This is fine, 0. This is fine, -1. This is the issue because this is left side is 2, right side is 2, 0. 2 minus 0 is 2. So this is violation. This is violation, and you can see it's dog foot, scenario 1. So that means we have to do 2 rotations. We need to do 2 rotations, right? The first rotation is done here to make it left, and then second rotation is done here. So let's do the left rotation. Meter madi, right? 20, 24, 15. So then 13 goes up and 10 goes down. And you can see still this is binary surgery. 10, 13, 15, 20, 24. Still the issue is here. But now we have make it left issue. Earlier it is left. Now you need to do the right rotation. So then it is 20, 24, 13 will go up, 10 will also come up, and 50 will go there. Now it is balance, back in the balance situation. Now I can insert 7. So we can insert 7 as a left child of 10. Still no issue. This is 1, sorry, 0, 1. Okay. This is 1, 2 minus 1. We have issue here. Because this is 1, 2, 3. 3 minus 1 is 2. 2 is not balanced. Violation. And this is, remember the issue is here. It is left situation. Left situation. You look at the issue side. This is the issue. Issue is because of this. So therefore it's left situation. So therefore we can do a single rotation and fix it. Right? So that rotation is done here. Right rotation. Okay. So therefore 13 will come up. 20 will go down. 24 will be going up, down. And this 15, you need to pass it to the 20. You need to pass it. Okay. So then 10 will come up. 7 will come up. Now it is sorted. 7, 10, 13, 15, 20, 25, and also balance. Okay. Right. So now we can add 30. So 30 is bigger than 13, bigger than 20, bigger than 24. So it's here. You can see how much of a time it takes, right? So you need to do entire paper in 1 hour, right? Second paper. Now this is fine. This is fine. This is also fine because 1 minus 2 is -1. But this is not. This is also fine, right? Because 2 minus 3 is -1. 1, 2, 1, 2, 3. Okay, so this is still fine. So this is balance. Now I can add 36. So once you add 36, now it is not balance. Right? Now it is not balance. Where issue? Issue is here. Right? Because this is 0 minus 2 minus 2. But this is right situation. So therefore we just need to do single rotation. Single rotation on here. Okay. Single rotation here. So let me erase somewhere because I have no space here. Okay. Right. So then this is 13, 10, 7, 20, 15, and we are doing the right rotation. Sorry, left rotation. 30 will go up. and 24 goes down. And what is this? 36 will come up. Right, so now it's balanced. Now we need to add 25. So 25 is bigger than 13, bigger than 20, lesser than 30, bigger than 24, somewhere here. Now there should be violation, right? So this is fine, this is fine, this is fine because 2 minus 1 is 1, but this is the issue. Because this is 1 minus 1, 2, 3, 1 minus 3 is minus 2. This is the violation. And the violation is here, okay, here. So therefore it is right, left violation, because violation is due to this node, right? Don't think that it's right. No, it's right, left, because violation is due to this node. Okay. So that means you need to first do a right rotation. Okay. So then only you can do the left rotation. So this is a very difficult question. Difficult question means it's time consuming question. Okay. So ඉස්සරහ කොහේ හරි වැරද්දක් කරා නම් දැන් ඔක්කොම මේ වෙලාව ඔක්කොම අපතේ යනවා. ලකුණු හම්බෙන්නේ නැහැ අපිට. I hope I have not made any mistake. Okay. Right. So the issue is here, and it is right, left. So therefore now we are going to fix it here because this is our first rotation. First rotation එක කරන්නේ ලෙඩේ තියෙන තැනට යටි. ඊට පස්සේ තමයි ලෙඩේ තියෙන තැනට බෙහෙත් දෙන්නේ. Yeah? So therefore you need to do the rotation here, right? And it must, by now the idea is make it right. So therefore you need to do the right rotation. Okay, right rotation. So then the result is 13, 10, 7, 20, 15, 24 will come here, and 36 will go down, and 25, you need to pass it to 30, because this guy is the right child, so you must pass it to 30. 25. Okay, so remember this guy must be passed to this guy. Now still the issue is there because we just did the first rotation. Now you need to fix the issue in here because still the issue is there. Now you can do, this is the right rotation. Now you can do the left rotation. Right, left rotation. So then you have 13, 10, 7, and you are doing the right left rotation. So therefore 24 will come up, right? And 20 goes down, 15 also going down, and 36 also coming up. You need to pass this guy to this guy, right? Left of 24 will be the right of 20. Now it's again balanced and sorted. 7, 10, 13, 15, 20. Oh, how comes 25 here? So you can't have 25 here, right? This is fine. 24 goes, 24 goes there. 36 goes up. 20, because 25 can't be left side, right? We need to pass this as a, remember when you do this rotation, you need to pass this right child as the left child of 30. Left child of 30. And where is 30? මම මෙතන මොකක් හරි උඩ පටයක් කරලා තියෙනවා. හරි පොඩ්ඩක් ඉන්න. 30ට වෙච්ච දේකුත් නැහැ. Right. 7, 10, 13 is fine. 20 is fine. Right. 15 is fine. So 24 goes there. 36 goes down. Right. 24 goes there. 30 goes down. 30 must be here. So what happened to my 30? So 30 is here. And 36 goes down, right? Okay. And now when you are 24 goes there, you need to pass this guy as the left child of 36. 30, left child of 30, right? So 24 goes there. When you go down, this guy must be given to this guy. So therefore, no 25 here. Oh, right? No 25 here. We must pass that 25 to 30. 25 to 30. Right. So now we need to fix this point, okay, by doing the left rotation because issue is this side now. Okay, so let's 7, 10, 13 is fine, but we need to fix this now. Your 24 goes up, right, and 20 goes there. 15 will be here, right? So then 30 will be here, 25 is here, and 36 is here. So there's nothing to pass. Pass කරන්නේ මෙතන තිබුණා නම් හරි මෙතනින් නෑ pass කරන්නේ නෑ මේ පැත්තට. මෙතන තිබුණා නම් දැන් pass කරන්න ඕනේ මේ පැත්තට. 20 දෙන්නේ. So now it is again sorted 7, 10, 13, 15, 20, 24, 25, 30, 36 and it's balanced. So this is 0, this is 0, this is 0, this is 1, sorry, -1. Right, that is fine. So this is my final result. 7, 10, 13, but let's see the examiner's answer. 7, 10, 13, 24, 20, 30, 15, 25, 36. Correct. Right, exactly my answer. Okay. 13, 10, 24, 7, 20, 15, 30, 25, 36. right? වැඩේ දන්නවනම් බය නැතුව කරගෙන යන්න තියෙන්නේ. මිස්ටේක් එකක් වුණොත් ඉතින් කරන්න දෙයක් නැහැ. මනුස්සයෝ විදිහට අපේ අතින් වැරද්දක් වෙන්න පුළුවන්. හැබැයි ලොජික් එකේ වරද්දන්න බෑ. ලොජික් එක දැනගෙන කරන්න. මනුස්සයෙක් විදිහට වැරද්දක් වුණොත් ඉතින් කරන්න දෙයක් නැහැ. ඉතින් ඒකේ ලක්ෂණ දෙක නැති වෙයි යාට හරි. But you must know what you are doing. Okay. Right. So that is how you do it, right? So this is the type of questions you get in the exam. මේවට වෙන කෙටි ක්‍රම නැහැ. හරි. කෙටි ක්‍රම නැහැ. AVL එක ගන්න ඕම තමයි. හරි. So 6 marks. Okay, 6 marks. ඊට කලින් මොනවද අහලා තියෙන්නේ? right, in order traversal. ඉතින් මේකට වෙලා යන්නේ නැහැ. හරි අරකට වෙලාව ගන්න පුළුවන්. right. right, quick sort එකක් ගැන කියලා තියෙනවා. right, හරි ඉතින් මේක විතර වෙලා යන්නේ මේකට paper question. right, so this won't take much time, right? Yes. So you can do this question in 15 minutes. 15 minutes. This is also very easy question. You have two questions. That means one question 15 minutes. Okay. So that means, sorry, one question 30 minutes. Sorry, 30 minutes. Okay. 30 minutes, 30 minutes, 1 hour, 2 hour. That is 1 hour for the second paper, right? You have only two questions. Two questions. 1 hour. So that means one question 30 minutes. Of course, that is why the other questions are easy. So you can take about 10, 15 minutes to do the AVL question. Other 15 minutes, you can do the rest of the questions in that part. Okay. So then the other question, again, you have a half an hour. Right. Any questions? Any questions about binary, AVL trees? Special case of a binary search tree? Okay, so let's move on to our next subtopic. This is our last subtopic under binary under trees, binary heap. So far we have been discussing on binary search tree. Now that's the end of the binary search tree. I told you that we are going to look at two special cases of binary trees. One is binary search tree, other one is binary heap. And special case of binary search tree is balanced binary search tree. That is AVL tree. Okay. So just keep that big picture. Special type of tree is binary tree. Special type of binary tree is binary search tree and binary heap. And special type of binary search tree is balanced binary search tree. In our case, it is AVL tree. So in binary search tree, data is sorted from left to right. In binary heap, data is sorted from top to bottom. Okay. And still it's a binary tree. Right? Special type of binary tree. Right? Right. So binary heap. So binary search tree is related to searching. And binary heap is related to sorting. Okay, sorting. Right. So what is a binary tree? Sorry, binary heap. Binary heap is a binary tree that is sorted from top to bottom. Okay. And if it is sorted from smaller to bigger, we call it min heap. Then the smallest is here. If you sort it from biggest to smaller, that means the biggest value is here, then it's a max heap. Right? It's just a matter of whether you sort it ascending order, descending order. Other than that, heap is a heap. Okay, heap is a heap. Okay. Right. So if it is a binary heap, it must preserve two properties. One property I have already mentioned, that is, it must be sorted from top to bottom. So that is called heap property. That is called heap property. But there's another property you need to preserve to make it a binary heap, that is called shape property. Right? So the shape property says the tree must be complete binary tree. Right? It must be a complete binary tree. What is now? Oh, I have already explained what is complete binary tree, right? Remember in the very first session we discussed about binary trees, complete tree, full tree, and so on. So what is a complete tree? So let's get back to complete tree. Remember complete binary tree, special type of binary trees. So complete binary tree is a binary tree where all levels except possibly the last level are completely full, and the last level has all its nodes filled from left to right. Okay, left to right. So last level, your nodes fill from left to right. So the next node will be here, 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 and so on. Okay, and next it will be again from here, here. So that is how it will keep growing. Right. So then we say it's a complete binary tree. Complete binary tree. So that must also be satisfied. Right. So that is called shape property. So that is called shape property. Right. So now let's see how to do insert, remove the root, and remove any other node operations. So what are the operations we are interested? We are not interested in anything like searching and so on, because binary heap is for sorting, not for searching. Okay. Right. How to insert to a binary heap? So when you insert a new data or new node, you always insert into the last level, preserving the shape property. Right? Always we insert it to last level, preserving the shape property. So that means it must be filled from left to right in the bottom lowest layer. Right? So that is your step number one. Now, when you do that, it will violate the heap property. It may violate heap property. Remember that your data must be sorted from top to bottom. Now you need to fix that by something called Okay, swapping. You need to keep swapping from bottom to top until your heap property is preserved. Then you are done. Then you are done. That is how you do insert. It's not, I told you binary heap is very easy. So let's take an example. Okay. So let's keep building our binary heap, right? We'll keep inserting. So every time you insert, first make sure you preserve the complete or the shape property, then you preserve the heap property. Then you go to the next step. Right, insert 50. Obviously, you can insert it because that is your first node. Nothing to do, right? Next, let's say we want to insert 30. So remember, first we preserve the shape property, then we preserve the heap property. So in order to preserve the shape property, you need to add it as a left child, right? Because you need to add from left to right. Okay, so that is your step number one. Say, okay, so let's assume this is a max heap. So then this is bigger than this, so therefore shape property is preserved, heap property is also preserved. Nothing to right? You don't need to do anything. Let's assume this is a max heap, okay? Right, so now you want to insert 80. So how do you insert? First insert it preserving the shape property. That means you go from left to right in the last level. Now you need to double check whether it has violated heap property. Of course, yes, because 80 is bigger than 50. It must be sorted from top to bottom because I told you we are going to create a max heap. Right? Now it has been violated. So therefore you need to do a swapping. Right? Swapping with your top one. So then it will be 80, 30, 50. And that's the end of inserting 80. Okay, inserting 80. Right? Swap this, 80 will go up. Okay. This is super simple thing, okay? Say, let's say we want to insert 40. So again, we insert it, preserving the shape property. So therefore 40 will be this. Now you need to check whether it has violated heap property. It must be sorted from top to bottom, right? So 40 is bigger than 30, so therefore you need to swap it. So then it will be 40 here and 30 here. And that is our final state after inserting 40. This is clear because this is super simple, right? Say now we want to insert another data, 90. So first we insert preserving the shape property. So therefore 90 will be here. And now you need to check the heap property. You check it from your node upwards. Okay, so 90 is bigger than 40, so swap it. 40 goes down, 90 goes up. Then again you need to check with its parent. Yes, 90 is bigger than 80, so therefore 90 goes up, 80 goes down. So the result is 90 here, 80 here, and 40 here. Okay. Simple as that. So first we swap these two, then we swap these two. You need to do it until your heap property is preserved. And you keep doing like that. Keep doing like that. Okay, so you only thing is it must be sorted from top to bottom. So you don't need to worry about now you can see this is 80, this is 50. Of course, 80 is bigger than 50. No, you don't need to worry about that. So that is binary search tree where you go from left to right sorted, right? So don't worry, this is 80, this is 50 is perfectly fine. Or whether this is 50, this is 80 is also fine. Because the only thing is, if you take a node it's below node must be smaller than that. If you take a node, it's below node must be so smaller than that. We don't care whether 40 here, 30 here, or whatever. Okay, so we care about sorting in this way. So when you insert it first with preserving the shape property and then check and fix the heap property, you keep having the binary heap. Again, the idea is then and there fix it rather than wait for a lot of violations. Right. Any questions? Because we are done with how to insert or how to make a binary heap. Right. So now, how to remove the root? How to remove the root? So there's a specific approach. This is how you remove the root. You replace your root because you are going to take out the root with the rightmost leaf of the last level. That is usually the last inserted value, unless you have done any swapping. Right? You replace it with the last level rightmost value. Then you need to preserve the heap property. So why do you take the last level uh, rightmost value? Can anyone give me an answer? So when you want to delete your root, what we do is, say we replace it we are going to take it out, we are going to replace it with this value. This will be here now. Why do we do like that? Any idea? Why do you want to replace that with this last level rightmost node? Because everything has a logic. So that is to preserve the shape property. Remember, binary heap always make sure that it has satisfied the shape property and heap property. So if you replace it with the last level rightmost node, your root, then you have again preserve your heap property. Sorry, shape property. But now most probably you have violated heap property. So therefore, now you need to do the swapping and take it down until your heap property is preserved. Okay. Heap property is preserved. That means again you need to take it down to the correct level. So then you are done. Now it's back. It's again a heap having shape property preserved and heap property preserved. And this is how you do it. You keep taking from the root like this. So then someone will ask, why do you want to keep taking from the root? When you keep taking from the root, basically you are getting the data in sorted order. So that is why this is the basis for binary sort. Sorry, by heap sort. Heap sort. So you add your data into binary heap using the logic I explained how to insert. Then you keep taking data from root, and the final result is now you have received your data in sorted order. If it is a max heap, you have got the data in descending order. If it is a min heap, you have got the data in ascending order. Because purpose of binary heap is sort your data. So let's take an example. Say this is my root. I want to remove 90. So you replace 90 with 55. replace 90 with 55. Why 55? Because then you preserve the shape property. But now you need to check your next level and fix if we have any violation of heap property. Obviously, 55 is smaller than, remember this is a max heap. 55 is smaller than 85 and 80. So therefore you need to do a step. So then you need to think, are you going to do step in this way or that way? Because both are bigger than 55. Now can someone tell me which one you want to step? Do you want to step this one or this one? Or what is your logic? What is your logic?
Left side
Why?
to preserve the shape.
Preserve the shape.
That's
If you
from
step,
left.
shape property is preserved, right? So which one you want to step and what is your logic? Are you going to step with left one or right one in this case? Okay. Or I'm asking this, are you going to step with 85 or are you going to step with 80?
85.
Why?
Because if we swap to 80,
Hmm.
then if it is a small value, then we need to add to the this side, so it won't preserve the shape. So
Yeah.
if we
Yeah.
add in the left side,
Yeah, that is correct. So if you step with 80, so then the result is 80 here, 55 here. But again, it has violated heap property because 85 is bigger. So then again, you need to step it, right? With 85 here and 80 here. So therefore, so the better option is you look at the bigger guy and swap it. So then you just need to swap only once because otherwise again you need to swap. So out of these, the bigger guy is 85. So therefore you can swap with 85. Okay. But again, you need to check, right? Now you can see that 55 is 70 and 60 both are bigger. So therefore you need to find the bigger guy and swap it again. So 70 here, 55 here. Now that is fine because these guys are smaller. So this is your final result. So likewise, you keep doing this until your binary heap is empty. So by the time your binary heap is empty, you have given data in sorted order. Right? So basically you build the binary heap and keep taking from the heap root until your heap is empty. So that means you have given the data in sorted order. Okay? Sorted order. Is it clear? So that is how binary heap okay? You just keep inserting your data to be sorted and you then keep taking from your root, but according to that logic, so that result is you have given the data in sorted order. And if you want to sort it in ascending order, make sure you build a min heap. If you want to sort it in descending order, make sure you give it in build the max heap. Or else, of course, you use the min heap and then reverse the data. But easier thing is just go for the max heap. Okay. And this is called heap sort algorithm. So already we have done one sorting algorithm, heap sort. We have already done one searching algorithm, binary search. Okay, binary search. Right. So now we are done with binary trees.
So what do you mean by heap sort algorithm?
So heap sort algorithm means we sort the data. So any sorting algorithm will sort the data in ascending order or descending order. So the result is your data is now sorted. If it is a min heap, then when you have removed all the data from the root, you have got the data in ascending order. If it is a max heap you created at the beginning, what you have received is data in descending order. So we have discussed about binary search tree, and also we have discussed about binary heap. So now we are done with binary trees. Even binary trees are special type of trees. And binary search tree and binary heap trees two special type of binary trees. Remember, not every tree is a binary tree. So you can have binary tree means you can have maximum 2 children for a given node. But there can be situation where you need more than 2 children. So that means it's a normal tree. It's not restricted to binary. And those normal trees are called B trees. B trees. That means it's not necessarily binary tree. It can be having 3 children, 4 children, and so on. Okay. So therefore, in B trees, there's no prerequisite saying it must be binary. No, it can be more than 2. Okay. And also, if it is a B tree, we want to make it balanced. Now you know why we want to make it balanced, because balancing make it searching faster. With few hops, you find it, or you know that that data is not there. That is why we want to make it balanced. Okay. Again, we can use certain algorithms, logic to make it balanced. So usually when you insert, it will do the self-balancing. Self-balancing means implement a particular algorithm to check whether it's not balanced and then fix it, and make it balanced. But not a balanced binary tree, balanced non-binary tree. And we call it B tree. B tree is a tree which can have more than 2 children per node, and also it is balanced. Okay. So we call it by B trees. B trees. But there are some differences when it comes to B trees. Actually, examiners have not asked much about B trees so far. So I hope they will continue that. So therefore, I'm not going to discuss a lot of things about B trees. But if you are really interested, uh, do a Google search, go to YouTube, talk with your chat GPT. If you are really interested more about B trees, okay. So these B trees are used heavily in indexing, database index, or file indexes. There are different type of indexes like hash index, linked index, and this is another popular type of index is B tree index. Okay. So unlike the normal binary trees, it grows from the root, top to bottom, not bottom to top. Okay, so the new data is added to the root. No, now usually we add it to the leaves. But in B trees, we add it to the top, and then depending on the requirements, you need to restructure it. So that restructuring logic can be vary depending on your requirement. So therefore, we are not going to look at the exact restructuring algorithms. Okay. But why do you want to restructure? Because we want to make it balanced. Okay. So B trees are mostly used in indexes, handling data records and so on. So the time complexity of B tree is also log n or log 2n, which is fairly good for search, insert, delete. Okay. Right. So that's it. Right. So there are some past paper questions related to binary trees, binary heap as well. For the data structures and algorithm, I recommend you to do at least 7 years of past papers. Right? At least 7 years of past papers. Because you will learn something new and a possible new another model of questions. Another model of questions. Right. So now we are done with trees. We are done with trees. Okay. So remember we kept 2 questions in the data management. Right. So we'll take a small break and do that so that we can mark this as done. Okay. Distributed databases as done, because otherwise we are keeping those pending. Okay. I don't want to keep those things pending forever. Right. So we'll take a small break. After the break, we'll do those past papers, right, related to data management. Okay, so let's continue. Right, so let's move on to 2024 question 1C. C, D, and E. Describe 2 advantages of distributed database systems over centralized database systems. So that, of course, we have discussed, right? So high availability, fault tolerance, scalability. Okay. So we have discussed about those, right? Even it can improve performance because we can keep your data near you, right? So that you should be able to explain. D1, briefly explain peer-to-peer replication and master-slave replication. So you need to very clearly highlight in master-slave replication, the writes operations are done to the master and then master propagate it to slaves, and read operations are done using slaves so that your workload is also distributed. Okay. Read operations are done from slaves and write operations are done to the master. And also you don't need to, you just need to explain how it is done. Okay. Not advantages, disadvantages. If you want, you can write a bit of advantage, disadvantage as well. Like the write operation lead to less conflict because everyone write to the same node. Okay. Peer-to-peer application, of course, you can do both read and write to any node. Both read and write to any node. And each peer need to synchronize with other peers. If there's a write operation, the peer need to synchronize it with the other peer nodes. Okay. So there's no single point of failure because in master slave, if master is down, you can't write. But here it's better scalability because there's nothing called master. So any node, if a particular node is down, maybe you can use another node as well. Okay, so likewise you need to explain, okay? But you need to highlight that peer-to-peer all nodes are equal weight. That means any node you can do read and write. Okay. But in master slave, master is responsible only for writing and slaves are responsible for the reading because master propagated to slaves. Okay. Right. Third one. State one advantage and one disadvantage of peer-to-peer replication compared to master-slave replication. Right. One advantage of peer-to-peer. Obviously, there's no central point of failure now because any node can be used for read and write. And it's better scalability also. So the disadvantage of peer-to-peer, so there can be some complexities because each peer need to synchronize with all the other peers. Unlike the master slave, where master does all the synchronization. Okay. So likewise, you need to write 2.1. When they ask for 1 point, maybe you can write 2 points each. Okay. Right. So this is E part. Right. So this is a huge question, 12 marks. So these questions you can see very less mark, right? 2 marks, 4 marks, 4 marks. But here you have 12 marks. 12 marks. Right. So let's read it. I gave you time for you to do it also. Consider the 3 relations related to shop global reads. Make sure you pay attention to each and every word, okay? Global reads, which has 3 branches operating across 3 locations, Kandy, Mathura, Jaffna. So 3 locations, 3 sites. The bookstore has set up 3 computer sites called Site 1, Site 2, Site 3. 1 for each location. So that means Kandy Site 1, Mathura Site 2, and maybe Jaffna Site 3. The data access requirement vary by site. So that means different sites have different requirements. And the customer and purchase relations are fragmented and replicated to meet the data access requirement of each site. So that means we have 2 relations or tables, customer and purchase. Customer, purchase, and those are fragmented. Okay, and replicated also. That means redundant data, duplicated. Primary keys are underlined and the foreign keys are italics. So these are the primary keys and these are the foreign keys, italics. Okay. So here foreign key is branch name because branch name is the primary key. So this is basically a connecting table, right? Many-to-many connecting table. So that is why you have the customer ID and branch name as the 2 foreign keys. Okay. So likewise, you need to understand this, right? You can take your time because you have 1 hour. Note, it looks like this is not fragmented because it says only customer and purchase tables are fragmented. Okay. Note, different locations such as Kandy, Mathura, and Jaffna are known as branch names. So basically, this branch name is Kandy, Mathura, Jaffna. Right? Data access requirements. Site 1, say site 1 is your Kandy, and that is also your head office. Okay, headquarters. Requires full access to all records in branch relation Right? Full access to branch relations. So Candy need full access to this. And need access to customers and purchase information specifically for Candy branch. For purchase and customer, they only need Candy branch data. But Candy branch need the full access to branch table because that is the headquarters. So then side 2, Madara, it require access only to the attributes such as customer ID, customer name, right? Customer ID, customer name, and branch name of customers, and branch name. Okay, so those are the 3 they need. Let me highlight. So they need customer ID, customer name, and branch name from the customer table. Okay. Of customers from Madara branch, right? So they are only interested in customers from Madara branch and only interested in customer ID, customer name, and branch name. Okay. And needs access to purchase information specifically for Madara branch. Purchase also only for Madara branch. So that means customers from Madara branch. Okay. Purchase related to customers from Madara branch. That means customer ID is related to Madara branch. Side 3, Jaffna. It requires access only to the attributes such as customer ID, customer name, and branch name. Same, right? Customer ID, customer name, branch name, same as Madara branch. Of customers from the Jaffna branch, again, they only need customer details about Jaffna branch. And need access to purchase information specifically for Jaffna branch. So that is also identical requirement. Madara and Jaffna has identical requirement. That means they only need customer ID, customer name, and branch name of their own customers and purchase details related to their customers. Okay. It looks like they don't need access to branch table. So branch table access is required only for the Candy, and it looks like they need the full all fields also, not just customer ID, customer name, and branch name. Okay, because there's nothing like that is mentioned. Right. Express the fragmentation conditions for each fragment using relational algebraic expression. That means you need to use sigma phi notation. Sigma phi notation. So this can be slightly different actually, depending on the way you look at it. Okay. Right. So let's look at the fragmentation. Okay. Right. So definitely we need to fragment the customer table based on sigma. That is sigma branch name is Madara, sigma branch name is Jaffna. You need to break it. That is horizontal fragmentation you need to do for customer table. Okay. So because branch name is basically Candy, Madara, and Jaffna. Okay. So here also we can do the same. Purchase also, right? Based on branch name. Like based on branch name, we can do it because they only need access to their purchases. At the same time, we need to do a vertical fragmentation because Madara and Jaffna only need access to these 3 fields. Right? Full access is required for Candy. So therefore, we can break it into 2 parts. This, and this, one relation. And of course, you need to duplicate the primary key. This, and this other part. So then both must be accessed by Candy, or they can simply access customer. But that sub part can be accessed by Jaffna and Mathur. That is because they are only interested in customer ID, customer name, and branch name, right? So you need to do horizontal fragmentation and vertical fragmentation. So there's nothing called this is the answer. As long as your fragmentation is reasonable, you should get the full marks. Okay. So that should be your answer. Okay. So 2 sigma base and 5 base, that is both selection based fragmentation, position based fragmentation. Okay. Right. So this is they have done the 5, right? So because you need only customer ID, customer name, and branch name. That is because we can use that one for Jaffna and Mathura queries. Okay, Jaffna and Mathura queries. When you do fragmentation, vertical fragmentation, make sure the rest of the stuff is also taken into a different relation, because otherwise that is lost. But with primary key as a common thing. So the rest of the stuff we have taken to other fragment. So that is a vertical fragmentation. Okay. So because Marker and Jafta will only use customer info, not this one, because they only need access to this. And then the Sigma can see customer info candy, customer info marker. That is based on Sigma. And purchase also we can do it because candy people, sorry, marker people are interested in customers related, purchase related to marker. So therefore we have the purchase candy, purchase marker, purchase Jaffna. Actually, I don't know whether we need purchase candy because it looks like candy need all the details, but yeah, maybe, yeah. So candy also they have make it purchase candy. Okay. So I thought candy need all the details. I thought of not breaking it to purchase candy, but because I think we break it into Martha and Jaffna, the rest of the stuff we can call it purchase candy. And of course, the customer info candy. But remember, they need the full access to department. Sorry, branch. Okay, full access to branch. So therefore, anyway, you don't need to fragment the branch because others are not interested in branch. Okay. So marks will be given for any correct answer because this is not the only way. Right, as I told you, maybe you can decide not to break it into candy separately because maybe candy need all the details. Okay, and so on. Because it doesn't say that candy need only candy related purchases, right? Yeah, it says, right, purchase information specifically for candy branch and customer specifically for candy branch. Yeah, so you need to do that. Right, so therefore this is correct. Customer candy, purchase candy. So then customer info marker, customer info Jaffna because you need only those fields. Those fields. So here you are referring to the customer table, but here you are referring to the customer info table because Martha and Jaffna need only specific fields, but Candy need the full details. But purchase wise, they only need Candy purchase. They need only Martha purchase and Jaffna purchase. Okay. Right. So that is your question 1. Okay, question 1. So then we can do question. So then we can do question 2 also, right? So the question 1, C, D, E. C we did. Yeah, E also we did, right? Yeah. So yeah, this is transaction. So that's it for the 2024. Then we can do 2023 question 1A. 2023 question 1A. Second paper. That is a huge question, calculation question. 2023 question 1A. Yeah, this one. Okay. A, B, not only A, we can do B. Yeah, A and B. And even we can do C. Right? We can do C. Yeah, we can do A, B, C. Okay. Not just A. Like, yeah, A, B, C, all three. Right, so let's do that. And again, you take your time and read it. This is serious stuff. Okay. Right. Consider the statement: distributed databases can offer enhanced availability compared to a single centralized database. Do you agree with the given statement? Justify your answer. Of course, yes, right? Because in centralized database, you have only one site, one mesh, one server. If that is down, no one has the functionalities. But in distributed databases, we have multiple sites, either all are peers or master slaves. So that means higher availability. If one site is down, you will be directed to another site. Okay. So there is higher availability. Okay. And also higher performance also, but you just need to mention about the availability. Okay. So you have redundant sites, multiple sites. So failure of one database fragment will only affect that others still have the access. And not only that, failure of one fragment can be redirected to another site also. That is another possibility. Right. So that is A part. B part. Consider the following database schema of software company, which consists of two relations, project and client. So you have two tables, project table, client table. Right? Project and client are stored in node 1, node 2, and node 2 respectively. The results will be stored in node 3. So that means you have the node 1, node 2, and results are needed in the node 3. Okay. So we did similar question. The results will be stored in node 3. So these are the two tables, project and client. Primary keys are underlined. Yeah. Client name is there, email, contact number, location, project name, destination. It looks like there's no connection between these, right? Yes, client ID is there. Right? Client ID is there. So therefore, there's a relationship, right? There's a connection. So that means your project has a client. Project has a client, okay? So possibly a project has one client, but one client can have many projects. This is one to many, okay? One to many. Right, notes. Client ID in the client relation corresponds to the foreign key C. Yes. So it says client CID. So CID is a foreign key. It's already explained also. Okay. That then the project contains 3,000 records. So this contains 3,000 records. Each record is 40 bytes. Right. Project ID is 10 byte. Project name is 10 byte. Duration is 5 byte. And budget 5 byte. Okay. CID is 10 bytes. Okay. What else? Relation client contains 1200 records. 1200 records. Each record is 50 bytes. Each record is full width is 50 bytes. Okay. Client ID 10 bytes. Client name 10 bytes. Email 10 bytes. Contact number 10 byte. And location 10 byte. Right. All the details are given. Okay. 30% of the projects have budget greater than 500,000. So where's the budget? Yeah, budget is this. And 30% has the budget bigger than 500,000. Right, bigger than 500,000. 30% of the projects. Okay. So usually that means your query has something to do with that. Yeah, you can see your query has that. That is why they have given it. Okay. Right. What else? So that means 30% of the projects will have budget bigger than this. Okay. What else? Anything else? Consider distributed query D below. This is the query. To retrieve the names of the project, right, project name, duration, budget, okay, name of the project clients, that is from client table, and the contact number of those clients for the project which have budget greater than 500,000. Right. So that means you need to get some details from project table and client table and do a join. Right. And you need to restrict. You don't need all the project details, only project which has a budget bigger than 500,000. Okay, 500,000. Right. Write 3 strategies to execute the distributed query D and calculate the bytes that need to be transferred to in each state strategy. So obvious, right? So the easiest one is what? You take data from here to here to here, right? No optimization. No optimization. Okay. So therefore, so let's say strategy 1, you take all the client details. So that means 1200 into 50. 1200 into 50 bytes. Plus that is you are getting from here. But here you know that there's a sigma that we can use because we need only projects having budget more than 500,000. And your question says 30% of the projects have budget more than 500,000. So that means you are not going to get 1,200 records. Sorry, 3,000 records. Only 30% of that. And then each record is 40. So that means 3,000 into, because we are going to get only 30% of the record. Right? 3,000 into 30%. And each record is 40. So that is our total thing, right? 3,000 into 40, right? 3,000 into 40. So what about the, they have not even taken the 30%, right? So this is 1,200 into 50. I thought they take only 30% of that. It looks like that optimization is also not done. I don't know why, right? So that is 100,200 into 50 is there. But here they have taken 30,000 into, so entire thing. So that means you can see it's not at all optimized. Not at all optimized. I don't know why, right? So they have not even take that part. Yes, right. So we should have done it, right? Because budget is there. Yeah, you don't need client details to do that sigma. So that is strange, right? So that maybe because the query is executed here, joins and everything. So therefore, examiner may be thinking like, you can't do any these nodes are very dumb nodes. Even you can't do sigma. Maybe that kind of a thinking is there, right? So that is why they have not even taken the 30% of the record. So these are just dumb terminals where you get all the records, and here you do everything. So therefore they have not even considered this part. Okay. So that is 1,200 into 50 plus 300,000 into 40. Okay. So the total is 180,000 bytes. Okay, 180,000 bytes. Is it clear? Right, so that is strategy one. No, it's a very dumb strategy. No optimization at all. So then we can do maybe N1 to N2, do the join and take it here. The third one is N2 to N1, do the join and take it here. Okay. Now you can do it in a smart way. Smart way. Okay. So this is your strategy two then. Transfer data in project table to node 2 and then execute the join and send the result back. Right. So now you can take your project details to the client. Right. So they have taken all 3,000 into 40. Right. 3,000 records. Each record is 40 bytes. So that means they have not done any processing in this site. Processing is only happening here. So no selection, no projection here. So entire 3,000 into 40, that is 120,000. So entire 3,000 into 40 is taken here. That means no processing here. Right. So then here you take the client details also added. So that is why it is this 40. But now you have only 30% of the record. Okay. So therefore 120 is coming from there. Right. 120 is transfer from here to here. Then this is final transfer from here to here. That is 36,000. There you have done sigma and phi both. Sigma and phi both. Okay. So the examiner's thinking is only one place where you execute the query, you do all phi and sigma. Other places you don't do anything. Just blindly take all the data in that table. That is why in the first scenario, you all take all data here, because you are doing processing. That means the idea is here no processing. You take all the data. And here no processing here, but here you do the processing and get the final result. So then other way around, you are taking all the record from here to here and do the processing and take it back, right? So let's see the approach three. So that means you are taking all the client details to the project side. So what is the client side? How many we have client side? That is 120 into 50. Sorry, 1,200 into 50. Because no processing here now, because all processing will happen here. 0, 5 into 0, 0, 0, 10, 60,000, right? 0, 0, 0, 5 into 10. Yeah, 60,000 bytes will be transferred from here to here. Let's see whether we have 60,000. Approach 3. Yes. So that means entire records in this site is transferred to here. But here now you can do the processing. Okay. So here what we are getting is 40 byte. Remember we finally we need only 40 byte. Right? 40 byte. So that is your 60,000. Here we have only 40 byte. And also the number of record is 900 because we have only 30%. That is sigma. Right? Because we do on we get only 30% for the sigma. Right? So therefore it is 900 into 40. Right? 900 into 40. That is 36,000. Okay. So that is 96,000. Is it clear? So the examiners, you also go by that point. Okay. So in the first strategy, you take all the records here, nothing process here, entire table, and do the query here. So therefore, anyway, that is the highest cost. Second approach, you take all the records from here to here and do the processing and get the final result. So here you have done sigma and pi. Here nothing. Right? In the other approach, from here you take everything here and you do the sigma and pi and take it. So then that should be your thinking. Okay, that should be your thinking. Okay, so that means only one place you do the processing. Other places you don't do any processing. No sigma, no phi. Okay, no sigma, no phi. But in reality, of course, here also, if you want, you can do processing because these are also database management system. But this is the thinking behind the examiner's answers. So you just go by that. Is it clear? Is it clear? Okay. Right. So then the C part also we can do. C part because it's a fragmentation question. A fragmentation question. But this one is not related to distributed databases. Okay. So let's do the third C part also. Then we are done. Consider the student relation given below related to the next gen university. The university is organized into three functional units: administration, engineering, and arts. Okay, administration, right? Admin, engineering, and arts. That is site 1, site 2, site 3. One for each functional unit. The data access requirement vary for each of these sites. It is important to note that the administration is not considered as a department. So that is this. Okay. And there are only two departments, engineering and arts. So engineering and arts are departments. This is not a department. Okay. Site 1 is not a department. It's administration. Okay. The student's relation is fragmented and replicated in a way to address the data access requirement of the next gen university. The primary key is underlined. So we have just one table, student table. The student ID is the primary key. Then you have the student name, guardian name, contact number, specialization, GPA, and department name. Okay. Right. So this is the data access requirement. Site 1 is dedicated to handling university's administration function because there is admin department. The site is primarily responsible for accessing, managing students' personal details. So it's only interested in personal details, including the student name, guardian name, and contact number. So that means we are going to have vertical fragmentation. For this one, they are going to keep only student name, guardian name, and contact number. Okay, student name, guardian name, contact number, but make sure you include student ID because that is the primary key. That is right. 5 student but you take only these student ID, student name, guardian name, and contact number. Okay, because they only need that, but they need for all both faculties because admin department is common. So don't do sigma, right? Site 2 and 3 are specially designated for the university's engineering and arts department respectively. These sites are expected to have frequent access to students' enrollment details of their respective departments. This information include student ID, of course, the primary key, specialization, GPA, and department name. Now, this is both vertical fragmentation and horizontal fragmentation. So these guys need only the sigma of student ID, student name, guardian name, and contact number, but no sigma, so only 5. But here, both sigma and 5, sigma is for the department name, 5 is you are only interested in these fields. So it's mixed fragmentation, right? So first it is vertically fragmented for site 1 and this is site 2 and site 3. And site 2 and site 3, there's a horizontal fragmentation. This is site 2, this is site 3. And the common field is primary key. Okay. So write the fragmented condition for each fragment. Yes. So therefore, this is site 1. It's no sigma here, only 5 primary key and required fields. For these things, you have both sigma and 5. Okay, both sigma and 5. So department name is engineering. Here department name is art. But that is why they have taken it as student info, because this is where you have this is for the admin department, this is for the this is for the admin, this is for the departments. So then you consider this one because they need only GPA and other things. So therefore your horizontal fragmentation refer to this vertical fragment. And other vertical fragment is for the admin department. So that is student personal info. So this is for the admin department, right? And this vertical fragment is further subdivided into 2 horizontal fragments based on department name, right? So you first do the vertical fragmentation, this one and this one, and this vertical fragmentation is divided into 2 horizontal fragmentation using sigma. Okay, so you need to write it in a proper way. Okay, right, so that's it. Include how original relation would be reconstructed. So how do you reconstruct? You need to do a union because it's vertically fragmented things, you need to do a union. Okay. So horizontal fragmentation, you need to do a union because some records are here, some records are here. Okay. So then you need to do a join. For the vertical fragmentation, you need to do a join. Horizontal fragmentation, you need to do a union because you need these records as well as these records. So that is where you have the union, department in engineering and department arts. So that union will create this one. So then these are like now two tables because it's fragmented. Now you need to do a join, inner join. Okay, inner join. So this is very important question, right? So I think this question is really good one. It covers almost everything. Okay, covers almost everything. So remember, if it is horizontal fragmentation, if you need all the detail, you need to do a union. If there's a vertical fragmentation, now it is like two tables where the common field is primary key. So therefore you need to do a join. But first do the union so that this entire thing is there. Then that is why there are brackets. Okay. Right. So now I hope you have the idea. Okay. So I wanted to do these past paper questions early so that you have enough time to because not only you need to understand the subject, you need to understand the expectation of the examiner, right? For example, in the distribution query processing, the expectation is processing is happening only in one site. Other sites just dumbly send everything, right? Not doing any filtration, any sigma, any file. Okay, right. So now I hope it's very clear. Right, we stop at this point, right? Thank you.